Good evening, ma'am.
Good evening, sir. You can start now, sir.
Okay, we'll continue with the topic which we stopped from last, classes. The colloidal system. Different types of colloidal system we learned. Now, a colloidal system is an heterogeneous system. You should remember, any colloid for that matter, it is a heterogeneous system, which consists of two phases. One is dispersed phase. The other one is called as dispersed medium. Now, dispersed phase is defined as particle which is distributed in the dispersed medium is called as dispersed phase. Now, for an example, if we take smoke, smoke contains carbon particle. If it is distributed in air, smoke will be called as dispersed phase and air will be called as dispersed medium. Smoke is made of carbon particles. So carbon particle is distributed in air. Therefore, carbon particle will be called as dispersed phase and air will be called as dispersed medium. So colloidal system is a heterogeneous system which consists of dispersed phase and dispersed medium. Depending on the dispersed phase and dispersed medium, we have 8 types of colloidal system. 8 types of colloidal system. Now, before we could talk about the 8 types of colloidal system, gas is a dispersed phase and gas is a dispersed medium. It is not a colloid. It cannot form a colloid. Gas and gas cannot form a colloid. Dispersed phase is gas and dispersed medium is also a gas. This cannot form a colloidal solution because these forms a homogeneous mixture. Already we defined that a colloid is a heterogeneous mixture or heterogeneous system, but gases mix with each other in any proportion, forming a homogeneous mixture. So therefore, gas and gas cannot form a colloidal system. Now, for an example, oxygen 21% and nitrogen 79%. The atmospheric air contains around 21% oxygen and 79% nitrogen. We cannot call this as a colloidal system because gases, 21% of gas is in homogeneous system. It's homogeneous with nitrogen. It can mix with nitrogen to form a homogeneous mixture. Therefore, gas and gas cannot form a colloidal system. Now, that is why we are learning only 8 types of colloidal system. The 9th type of colloidal system, gas and gas, is not possible because it forms a homogeneous mixture. Now, coming to the different types of colloidal system, now the dispersed phase is liquid and the dispersed medium is gas. When the dispersed phase is liquid and the dispersed medium is gas, then we call that the name of the colloidal system as aerosol. Aerosol of liquids. Example, fog, clouds, mist, fine insecticide sprays, all these are an aerosol of liquids. So dispersed phase is liquid, dispersed medium is gas. Now the second one, dispersed phase is solid and the dispersed medium is gas. Solid particles are distributed in gas. They are called as aerosols of solids. They are called as aerosols of solids. Here is aerosol of liquid. In both, the dispersed phase is gas, dispersed medium is gas, but dispersed phase is different. In case of liquid, aerosol of liquid. In case of solid, it's called as aerosol of solid. An example is smoke, volcanic dust, haze. All these are examples for aerosol of solids, colloidal system. The third, dispersed phase is gas and dispersed medium is liquid. When the dispersed phase is gas and dispersed medium is liquid, it's called as a foam. The type of the colloidal system is called as a foam. Example for foam: soap lather, lemonade froth, foam, whipped cream, soda water. All these are examples for a colloidal system called as foam. Soda water contains carbon dioxide in water. So carbon dioxide in water is also an example for a colloidal system in which the dispersed phase is gas and dispersed medium is liquid. Now, this is important. If the dispersed phase is liquid and the dispersed medium is also liquid, then we call those colloidal system as emulsion. We call those colloidal system as emulsion. Example for emulsion: milk, emulsified oils, medicines. They can ask you, what is an emulsion? So you should tell emulsion is a colloidal system in which the dispersed phase is liquid. The dispersed medium is also liquid. The next is also important. If the dispersed phase is solid and the dispersed medium is liquid, it is called as sols, S-O-L. So what is a sol now? A solid is a colloidal system in which the dispersed phase is solid and the dispersed medium is liquid. Example: paints, starch and water, proteins, gold salt, arsenic sulfide salt. All these are examples for a salt. And next we have is gas is a dispersed phase, solid is a dispersed medium. It is called a solid foam. It is called a solid foam. Example for solid foam: pumice stone, styrene rubber, foam rubber. All these are examples for solid foam. Next, dispersed phase is liquid and dispersed medium is a solid. This is also important. It is called as gels. Now, what is a gel? Gel is a colloidal system in which the dispersed phase is liquid and the dispersed medium is a solid. Example: cheese, butter, boot polish, jelly, curd. All these are examples for a gel. And the last eighth system is solid is a dispersed phase and solid is a dispersed medium. They are called as solid salts, or it's also called as colored glass. Example for the solid salt is ruby glass. Some gemstones, alloys, any alloys for that matter, is an example for a solid salt. Coming to the classification, this is based on the dispersed phase and dispersed medium. Now, classification based on the nature of interaction. This is also important. Interaction between dispersed phase and dispersed medium. So based on the interaction between dispersed phase and dispersed medium, colloidal systems are classified into two. One is called as lyophilic. The other one is called as lyophobic. Lyophilic. Philic stands for loving. Lyo stands for a solvent. So if it is water loving, it will be called as hydrophilic. It will be specifically called as hydrophilic. Phobia is fear, hating. So if a colloidal particle is having very less affinity towards the solvent, they are called as lyophobic. If the solvent is water, it is called as hydrophobic colloid. Hydrophobic colloid. So depending upon the interaction between the dispersed phase and dispersed medium, colloids are classified into two: lyophilic colloid and lyophobic colloid. What is a lyophilic colloid? Water-loving colloid. The colloidal solution in which the particles of the dispersed phase have great affinity for the dispersed medium is called as a lyophilic colloid. So a colloidal solution in which the dispersed phase have great affinity towards the dispersed medium. Whenever there is a strong interaction between the dispersed phase and dispersed medium, then we call those kind of colloidal system to be lyophilic colloids. Lyophilic colloids. Now, lyophobic colloids. Phobia stands for fear. Water-hating colloid. Now, what is this lyophobic colloid? The colloidal solution in which there is no affinity between the dispersed phase and the dispersed medium is called as a lyophobic colloid. A colloidal system in which There is no affinity. Now, for an example, if we take water, and in this water, if we have the gold particles, if you have gold particles like this of colloidal size 1 to 100 nanometer, this will be called as gold salt. It will be called as gold salt. Gold is a dispersed phase, water is a dispersed medium. It's called as gold salt. Now, gold is a metal and it does not have any interaction with water. Since gold has no interaction with water, this gold salt is an example for lyophobic colloid because the interaction with the dispersed phase and dispersed medium is minimum. Therefore, it's actually minimum or it's no. Therefore, this is called as a lyophobic colloid. So it is a 2-mark question for the 12th standard. Now, the difference between lyophilic and lyophobic colloids. The first one is so many differences are there. Few differences, if you can remember, that will be good. Now, surface tension. In case of lyophilic colloids, lyophilic salts, surface tension is lower than that of the medium. So surface tension of water or any solvent will be will be greater than that of a lyophilic colloid. In case of lyophobic colloids or lyophobic salts, so surface tension is same as that of the medium. Because this dispersed phase and dispersed medium has no interaction, the surface tension will also have no changes. So it will be same as the dispersed medium. The viscosity. In case of lyophilic salts, viscosity is much higher than the medium. Viscosity will be much higher than the medium. In case of lyophobic salts, viscosity will be same as that of medium. So lyophobic salts, viscosity will be same because no interaction between dispersed phase and dispersed medium, remember. Now, reversibility. Lyophilic salts are reversible. Lyophobic salts are irreversible. Lyophilic salts are more stable. Lyophobic salts are less stable. Visibility. Particles can't be detected even under ultramicroscope. So in case of lyophilic salts, particles cannot be detected even under ultramicroscope. Lyophobic salts, particles can be detected under ultramicroscope. Migration. Particle may migrate it in either direction or not migrate or do not migrate in an electric field because do not have any charge. So lyophilic colloid may or may not move towards the electrodes in the electric field because they do not have any charge. Particle migrates either towards cathode or anode in the presence of the electric field because they have charge. So lyophobic colloids are charged. Lyophobic colloids generally do not have charge. Addition of smaller quantity of electrolyte has little effect. In case of lyophilic colloids, addition of an electrolyte has smaller or little effect. Here, in case of lyophobic colloids, when you add an electrolyte, coagulation takes place. We will learn what is coagulation in a few minutes' time today. Next, hydration. Extensive hydration takes place in case of lyophilic colloids. No hydration takes place in case of lyophobic colloids. Example for lyophilic colloids: gum, gelatin, starch, protein, rubber. All these are lyophilic colloids, which has affinity towards the solvent. Metals like gold, silver, hydroxides like aluminum hydroxide, ferric hydroxide, metal sulfides like arsenic sulfide. All these are examples for lyophobic colloids. So we have lyophilic as well as lyophobic colloids. It is an important question. Distinguish or differentiate between lyophilic and lyophobic colloids. Now, classification, we have learned based on dispersed phase, dispersed medium. Second, we have learned based on the interaction between dispersed phase and dispersed medium. Now we're going to learn classification based on types of particles of the dispersed phase. Types of particles. Depending upon the type of particles of the different dispersed phase, the colloids are classified into multimolecular colloid, So this multimolecular colloid classification you do not have in the syllabus, but based on the particle of the dispersed phase, it is classified as multimolecular colloid. And it has different characters. We are not, we have different characters. We will not be learning those characters. So it's not important in case of, next is macromolecular colloid, multimolecular and macromolecular. Macromolecule means bigger molecular size. We do not have this classification. Now we have Michel formation. M-I-C-E-L-L-E-S. Micelles they call Michel, so pronunciation varies. So Michels are clusters or aggregated particles formed by the association of colloids in the solution. Michels are clusters of or aggregated particles formed by association of colloids in solution. The common example of Michels are soaps and detergent. Soaps and detergent. The formation of Michel takes place above a particular temperature called as Kraft's temperature, Tk. They represent as Tk, and above a particular concentration called as critical Michelization concentration, or it is just called as critical Michel concentration. So soap Michel formation takes place above a particular temperature called as Kraft's temperature and above a particular concentration called as critical Michel concentration, CMC. They are capable of forming ions. Michels may contain as many as 100 molecules or more. For example, sodium stearate, example of such type of molecule, is a typical example of such, sodium stearate is an example of soap Michel. When sodium stearate is dissolved in water, it gives Na plus and C17H35CO minus ion. This is called a stearate ion. C17H35CO minus is called a stearate ion. The stearate ion associate to form an ionic Michel of colloidal size. Ionic Michel of colloidal size. You can see this. You can see this. This is R groups. This is R groups. All are R groups. C17H35. Assume that this is R groups. Or see, if we take sodium stearate, RCONA, if you take C17H35CONA, this CO minus you will have, and you will have Na plus. This part, this Na plus will be lyophilic. It will have affinity towards water. This group is lyophobic. It will not have affinity towards water. Hydrophobic or hydrophilic, you can write. Since it does not have any affinity towards water, what happens is all the R groups will associate more than 100. So this is CO minus. This is CO minus. That is what they've written. COO minus. That's what they've shown here. And COO minus. Here also you have COO minus. It's a long chain. So we are representing the long chain like this. So when the concentration of the solution is below its critical Michel concentration. So if the concentration is below 10 power minus 3 mole per liter, it behaves as a normal electrolyte. But above this concentration, it is aggregated and it behaves like a Michel. So when it behaves like a Michel, the particle size is between 1 to 100 nanometers. All right. So you should remember. So Michel formation. So example for Michel formation is soap and detergents are the example for soap Michel formation. This soap Michel formation takes place above a particular temperature called as Kraft's temperature and above a particular concentration called as critical Michel concentration. Critical Michel concentration. So likewise, the main function of a soap is to reduce oily and greasy dirt to colloidal particles. The function of soap is to reduce the oil and greasy or dirt to colloidal particle, an emulsion. Soap, therefore, are known as emulsifying agent. The function of soap is to reduce oily and greasy dirt to the colloidal size particles. Therefore, soap is also called as emulsifying agents. Some other example of minerals are sodium palmitate, sodium lauryl sulfate, cetyl trimethyl ammonium bromide. All these you have to learn in a chapter called as polymers. In the organic chemistry, we also will learn something called as polymers. There we will be learning, not biomolecules. I think biomolecules, the chapter biomolecules, you'll be learning these things. Now, general methods of preparation of colloids. General method of preparation of colloids. Now, lyophilic and lyophobic colloidal solutions or salts are generally prepared by different types of method. Some of the common methods are given. Preparation of lyophilic colloids. So lyophobic and lyophilic colloids are salts. What is a salt? Dispersed phase is solid and dispersed medium is liquid. A colloidal system in which the dispersed phase is solid and the dispersed medium is liquid, those kind of colloidal solutions are called as salts. So common method of preparation. So we have learned the examples for lyophilic, lyophobic colloids. We've learned the difference between lyophilic, lyophobic colloids, all that. So we will not learn the four parts. So we'll directly go into the preparation of the lyophobic colloids. The first one, we learn the preparation of lyophobic colloids. Now, the first one is preparation of lyophobic colloids. Lyophobic colloids can be prepared mainly by two methods. One is condensation method. Condensation method. In this method, smaller particle size of dispersed phase are condensed suitably to be a colloidal size. This is done by the following method. What do you mean by condensation? Smaller size particles of dispersed phase are condensed suitably to be of colloidal size. The first one is by oxidation. A colloidal solution of sulfur can be obtained by bubbling oxygen through a solution of hydrogen sulfide. Now, hydrogen sulfide, in hydrogen sulfide, sulfur has -2 charge. Into a solution of hydrogen sulfide, if oxygen or any other oxidizing agent like nitric acid or bromine is bubbled, is allowed to react, this hydrogen sulfide gets oxidized to sulfur. The charge on sulfur is 0. This sulfur will have colloidal size. Sulfur will be of colloidal size. The first method is by oxidation. So a colloidal solution of sulfur can be obtained by bubbling oxygen through a solution of hydrogen sulfide, or by passing or allowing an oxidizing agent like nitric acid or bromine to react with hydrogen sulfide. The next one is by reduction. These all are condensation method. Reduction. A number of metals such as silver, gold, platinum have been obtained in colloidal state. By treating the aqueous solution of the salt with a suitable reducing agent such as formaldehyde, phenylhydrazine, hydrogen peroxide, stannous chloride. So by reduction also we can prepare a colloid, metal colloids. A number of metals such as silver, gold, and platinum can be obtained in colloidal state by treating the salts, aqueous solution of the salts, with a suitable reducing agent. Here, auric chloride. In case of auric chloride, gold is in +3 oxidation state. When this is allowed to react with stannic chloride, stannous chloride, SnCl2, what happens? This auric chloride will be reduced to gold salt. Here, Au, the charge on gold is 0. The stannous chloride will be oxidized to stannic chloride. So anything which undergoes oxidation will be called as a reducing agent. So here, tin chloride or stannous chloride is a reducing agent. So auric chloride is reduced by stannous chloride to gold colloid. Likewise, now the gold colloid, when reacted with formaldehyde solution, gold has oxidation number +3, formaldehyde. So it's gold auric chloride is reduced to gold of colloidal size, 1 to 100 nanometer, and you get formic acid. So aldehyde is oxidized to formic acid. Anything which undergoes oxidation is called as reducing agent. Here, the reducing agent is formaldehyde. So two methods we have learned. One is by oxidation, the other one is by reduction. The third method is by hydrolysis. Many salt solutions are rapidly hydrolyzed by boiling dilute solution of their salts. By boiling dilute solution of their salts. For example, ferric hydroxide and aluminum hydroxide are salts obtained by boiling solution of corresponding chlorides. So when you boil ferric chloride solution, we get ferric hydroxide colloidal salt. If you boil aluminum chloride, you will get aluminum hydroxide. So ferric hydroxide and aluminum hydroxide salts are formed by boiling solution of corresponding chlorides. Similarly, silicic acid salt is also obtained by hydrolysis of sodium silicate. The fourth method is by double decomposition. A salt of arsenic sulfide is obtained by passing hydrogen sulfide through a cold solution of arsenious oxide. So this is arsenious oxide, As2O3. This arsenious oxide, into this cold solution of arsenious oxide, if hydrogen sulfide is bubbled, we get arsenious sulfide. And we get the byproduct to be water, H2, 3 moles of water. So this is called as double decomposition reaction. So hydrogen sulfide also decomposes, arsenious oxide also will decompose to give arsenious sulfide. The next one is by excess cooling, a colloidal solution of ice in an organic solvent like ether or chloroform can be prepared by freezing a solution of water in the solvent. Molecules of water which can no longer be held in solution separately combines to form particles of colloidal size. So by excess cooling and by exchange of solvent, these two methods are not in our syllabus. So don't worry about it. This also is not there. Now, the first method what we learned is by condensation method. In condensation method, we learned oxidation, reduction, hydrolysis, and double decomposition. Now, the next method, what we have, 4 methods are there in the syllabus: oxidation, reduction, hydrolysis, double decomposition. Those 4 methods are called as, it comes under double decomposition. And let's see what comes under condensation method. The next what we have is dispersion method. In this method, large particles of the substances, suspensions, are broken into small particles, and this following methods are employed. It's called, one is mechanical dispersion. This mechanical dispersion we do not have in the syllabus, so I will not teach you. This is important. The second one is by electrical method, Bradig's arcs method. Very important question. Preparation of gold sol by Bradig's arcs method. Bradig's electric arcs method or Bradig's arcs method. Now, in a container, water is taken. In a container, water is taken. Into this water, 2 gold electrodes are immersed. 2 gold electrodes are immersed. These are called as gold electrodes. And these gold electrodes are connected to the power supply. Connected to the power supply. Now, this is water. Into this, we add little of sodium hydroxide or potassium hydroxide. We'll add a little of sodium hydroxide or potassium hydroxide. Now, this setup is kept in a container containing ice. This setup is kept in a container containing ice. Freezing mixture, ice and NaCl. It's freezing mixture. Freezing mixture. Now, on passing electricity, very high voltage, around 15 to 20,000 volts, very, very high voltage. And now, if you remember during rainy season or wind, when the two electrical wires comes into contact, the aluminum wires which carries current, when comes into contact, there will be a electric short. There will be a lot of energy dissipated when two wires come into contact. Sparks you would observe. Likewise, when these two electrodes are made to come into contact, an electric arc is obtained. Now, during this electric arc, what happens is the temperature developed is very high. Some amount of gold particles will vaporize. Because the temperature is very high, this gold will vaporize. This gold which vaporizes will condense and settle like this in the form of gold particles. This gold particle will be of the size 1 to 100 nanometers. Now, these gold particles are distributed in water. Therefore, this will be called as a gold solid. Now, what's the function of this NaOH or KOH? Now, if NaOH and KOH has two functions here. One is the stabilizing agent. Stabilizing agent is NaOH or KOH. What is the stabilizing agent? If NaOH or KOH is not there, what happens is this gold particle will settle at the bottom. It will form a suspension. In order to prevent the gold particle settling at the bottom, we use sodium hydroxide or a little of KOH, which acts as a stabilizing agent. And this sodium hydroxide or NaOH is also behaving like impurity in gold salt. Impurity in gold salt. Gold salt should contain gold particles and water, but it also contains Na plus ion, KOH, K plus ion, or OH minus ions. So therefore, this stabilizing agent itself will act as an impurity. So not only gold salt can be prepared by like this, any other metal salts, platinum, silver, copper, also can be prepared. Now, this method is used to prepare salts of platinum, silver, copper, or gold. The metal whose salt is to be prepared is made as two electrodes, which immersed in dispersion medium such as water. It is immersed in dispersion medium such as water. The dispersion medium is kept cooled by ice. The dispersion medium is kept cooled by ice, freezing mixture. Now, an electric arc is struck between the electrodes. We allow these electrodes to touch each other. So tremendous heat is generated by this method. And little amount of the electrode, gold, will vaporize and give a colloidal solution. The colloidal solution prepared is stabilized by adding small amount of KOH, or we can add NaOH also. And that itself acts as an impurity. This is called as dispersion method. So I have drawn the picture here. Any picture you can, and it's an important question. Brady's arcs method. The next method in case of dispersion method is called as peptidization. Now, what is this peptidization? It is a process of converting, important, this also is important, a process of converting freshly prepared precipitate into a colloidal form by addition of suitable electrolyte is called as peptization. What is peptization? A process of converting a freshly prepared precipitate into a colloid. Suitable electrolyte is called as peptization. Now, for an example, if you take ferric hydroxide precipitate, this is a freshly prepared precipitate. To this freshly prepared precipitate, we add electrolyte ferric chloride and mix it. So what happens is this precipitate will give colloidal size particles, and you will get ferric hydroxide colloid. Coming to the next concept, cause for peptization. Peptization is the adsorption of ions on the electrolyte by particles of the precipitate, and adsorption of ions of electrolyte. Important peptizing agents are sugar, gum, gelatin, and electrolytes. Now, example, a freshly prepared ferric hydroxide can be converted into colloidal state by shaking it with water containing Fe3, namely FeCl3 or ammonium hydroxide respectively. So ferric hydroxide precipitate, when shaken with ferric chloride, you get a ferric hydroxide colloidal solution. So this is ferric hydroxide precipitate. If we shake it with ferric ions, this ferric ions will get adsorbed on the surface of the ferric hydroxide. So colloidal particles of ferric hydroxide. A stable sol of stannic oxide is obtained by adding small amount of dilute HCl. Now, these all are not there in the syllabus. One example you can remember for peptization, that is freshly prepared ferric hydroxide. When shaken with ferric chloride, we get ferric hydroxide colloid. The next concept is purification of colloids. There's few methods of purification of colloids. All the methods given here in the NCERT is important. Now, the first method is dialysis. A process of separating the particles of colloid from those of crystalloids. We learned in the first class of this chapter, crystalloids are called as true solution. These true solutions are homogeneous mixture. True solutions are homogeneous mixture. Remember, a process of separating the particles of colloids from those of crystalloid by means of diffusion through a suitable membrane is called as dialysis. A process of separating the particles of colloid from those of crystalloids by means of diffusion through a suitable membrane is called as dialysis. Its principle is based upon the fact that colloidal particle cannot pass through the parchment paper or a cellophane membrane, while the ions of the electrolyte can pass through. Ions of the electrolyte are very small, they can pass through. Colloids has a particle size of 1 to 100 nanometer, they cannot pass through the parchment paper bag or cellophane or any semi-permeable membrane. The impurity slowly diffuses out of the bag, leaving behind the pure colloid. The distilled water is changed frequently to avoid accumulation of crystalloids, otherwise they may start diffusing back into the bag. Dialysis can be used for removing HCl from ferric hydroxide. Now, for an example, if you take a parchment paper bag, in this parchment paper bag, we have an impure colloid. We have an impure colloid. Now, this parchment paper bag containing an impure colloid is placed in a container containing water. One end you have water inlet, the other end we have water outlet. So what happens? Continuously, when you keep flushing it with water, what happens? Water will enter the bag or maybe the electrolytic impurities like Na plus and OH minus. In the preparation of gold salt, we understood the impurities is what Na plus and OH minus. Na plus and OH minus will diffuse out because only the electrolytic impurity can pass through it. The colloidal solution, gold particles cannot pass through it. So gold particles will remain. In order to purify gold salt, impurity is what? NaOH or KOH. How do you remove that NaOH or KOH? So you take the gold salt in a parchment paper bag or a cellophane membrane and you pass water, flush out with water. So what happens? The electrolytic impurities comes out of it. And this is a slow process. Now, the same process if we perform in the presence of an electrode, in the presence of an electrode, in the presence of an electrode, and it's called as electrodialysis. We have a parchment paper bag. Parchment paper bag containing an impure colloid. This is placed in a container containing water. And we have two electrodes. We have two electrodes, positive electrode and negative electrode. Now, Na plus will move towards the negative electrode. OH will come out of the parchment bag, go towards the positive electrode. And this process is a fast process. So it's the ordinary process of dialysis is slow. To increase the process of purification, the dialysis is carried out by applying electric field. The process is called as electrodialysis. The important application of electrodialysis process in the artificial kidney machine used for purification of blood of the patients whose kidneys have failed to work. The artificial kidney machine works on the principle of dialysis. So this is the principle in which the kidney machines work. People who are suffering from kidney diseases. The next method of purification is ultra purification. Salt particles directly pass through ordinary filter paper because the pores are more than 1 micrometer to 1,000 micrometer. Our colloidal particles is in nanometers, but here in case of ordinary filter paper, the pore size in the filter paper is micro. 1 micro to 1,000 micro. That means the pore size in the ordinary filter paper is bigger. Therefore, than the size of the salt particles. Therefore, we cannot purify it using or filter it using ordinary filter paper. If the pore size of the ordinary filter paper are made smaller by soaking the filter paper solution, a filter paper in a solution of gelatin of colloidal, and subsequently hardening by soaking it in formaldehyde, the treated filter paper may retain colloidal particles and allow only the true solution. So if the ordinary filter paper is soaked in the solution of gelatin of colloidal and subsequently hardened by soaking it in formaldehyde, this treated filter paper may retain the colloidal particles. Only the electrolytic impurity, true solutions will escape. Such filter paper is known as ultrafilter, and the process of separating colloids by using ultrafilters are known as ultrafiltration. Now, the last part of purification we will learn, and the properties of colloid we will learn in the next class. That's tomorrow. Now, ultracentrifugation. The salt particles just give me a moment. The salt particles are prevented from settling out under the action of gravity. The salt particles are prevented from settling out under the action of gravity by kinetic impacts of the molecules of the medium. The setting force can be enhanced by using high-speed centrifugal machines, having 15,000 or more revolutions per minute. Such machines are known as ultracentrifuges. So in higher classes, if you take up chemistry, you will know what is centrifuge, and the machine used to centrifuge all that. Now, this ultracentrifugation or ultrafiltration we do not have in our syllabus for 12th standard. We have dialysis and electrodialysis. Ultrafiltration is not, maybe you can learn ultrafiltration, but centrifugation is not there in your syllabus. So the next concept is properties of colloidal solution. We will learn the properties of colloidal, physical properties we will learn, chemical properties we will learn a little late, not the chemical, mechanical properties we will learn later. Now, the main characteristics, properties of colloidal solutions are as follows. Physical properties. Any colloid for that matter, they are heterogeneous in nature. Colloidal salts are heterogeneous in nature. They consist of two phases. We know that dispersed phase and dispersed medium. Stable nature. The colloidal solutions are quite stable. These particles are in state of motion and do not settle down at the bottom of the container. So if you take gold salt, these gold particles are in random motion. They do not settle down at the bottom. Filtrability. Colloidal particles are readily passed through ordinary filter papers. However, they can be retained by special filters known as ultra filters like parchment paper. Now, this colligative property, due to the formation of associated molecules, observed value of the colligative properties like a relative decrease in vapor pressure, elevation in boiling point, depression in freezing point, osmotic pressure are smaller than expected. So, since these particles, colloidal particles undergo association, these colligative properties will be always lesser than expected. For a given colloidal salt, the number of particles will be very small as compared to that of true solution. So mechanical properties we have to learn in detail. So we will not have time to continue with this Brownian moment, Tyndall effect, electrophoresis. All this we'll have to learn in detail. Electroosmosis, origin of charges, all that. So all that we will learn in the next class. So that's by tomorrow. Tomorrow we will learn and finish off the theory part of this chapter tomorrow, possibly. And we'll also solve some of the questions, simple questions we'll solve tomorrow. Ma'am, I'll stop the class, ma'am.
Okay, sir. Thank you, sir.